Hi guys, welcome back to the channel. In this lecture, we are going to discuss about the plastic collapse in frame structure. Okay, so we'll directly come to the problem. So in this problem, you are given this frame, okay, and this frame, we need to calculate the collapse value of this W. Okay, how much load is required basically to collapse this frame structure. Okay, as you can see that in this problem, this frame is basically unsymmetrical. Okay, unsymmetrical in geometry, okay, unsymmetrical in loading, right? So whenever we are whenever we need to calculate the plastic collapse load for beam or structure, first step we will be calculating the degree of static indeterminacy of that structure. Okay, so at first we will be calculating what is the degree of static indeterminacy of this structure. Okay, so at this point, at this support, A support, how much the reactions are, the reaction components will be one vertical reaction, one moment will be there, and one horizontal reaction. Similarly, at this E support, there will be one vertical reaction, one horizontal reaction, and one moment will be there, right? So total number of reactions are, are 6, okay, and equilibrium equation will be 3, okay, summation fx0, summation my0, and summation fy0, right? So degree of static indeterminacy will be 6 minus of 3, which is 3, right? So now, if degree of static indeterminacy is known to us, what is the number of plastic hinges? Number of plastic hinges required for collapse will be 3 plus 1. So that is equals to 4 plastic hinges are required for collapse of this structure. Okay, and next step will be to identify the location of plastic hinge. Okay, so in this frame you can see that where will be the peak bending moment occur? Peak bending moment will occur at A, at B, C, D and E. Okay, the peak bending moment will occur at the joints, right, or under the point load, or at the support. Okay, so there are 5 locations where the plastic hinge can form: A, B, C, D and E. Okay, so N is basically, capital L is basically number of plastic hinges can form. Okay, location of the plastic hinges, so that will be equals to 5. Okay, and degree of static indeterminacy is equals to, what you can say that is equals to 3. So independent mechanism will be 5 minus of 3, so that will be equals to 2, right? So for any collapse we need to have some mechanism, right? So independent mechanism will be 2 in this problem. So what are those independent mechanism and combined mechanism? Now we will discuss that thing. Okay, and that thing is very, very important. Okay, so you know what is the concept behind to calculate the degree of static indeterminacy. Okay, to know the places where the hinges will form, we need to identify those places where the plastic hinge can form, and that will be the places where the peak bending moment will occur. So peak bending moment will be occurring at these joints and under the point load and at this support. Okay, no doubt in this. So from here we found that independent mechanism are 2. Okay, so now let us discuss what is this independent mechanism. So basically, let us suppose consider this plastic frame, okay, this rectangular simple frame, right, which we are applying a load W at this point and W at this point. Okay, this frame is basically a symmetrical frame in geometry but unsymmetrical in loading. Okay, so and let us suppose MP is constant. plastic moment is constant, right, for the whole frame. Okay, so now if MP is constant, and again the static indeterminacy of this beam is ds equals to 3, right, it will be equals to 3, and an independent mechanism will be 2. Okay, so what are those two independent mechanisms? We will be understand that, we will see now. Okay, so first mechanism is basically beam mechanism. Beam mechanism. Okay, beam mechanism is what when there is a, okay, so what is beam mechanism? In the beam mechanism, the failure of structure will look like this. Under this point load, there is a formation of plastic hinge. One plastic hinge will form at this point, one plastic hinge will form at this point, okay, and one plastic hinge will form at this point. So this is basically a beam mechanism. Okay, now you can ask, sir, the total number of plastic hinges required for the collapse is 4, but here only 3 hinges are there. This is a partial collapse. This is partial collapse. Okay, partial collapse means the whole body is not failing. Their columns are okay. Only there is a mechanism in this beam, in this horizontal member. Okay, so this is what you can say, that this is beam mechanism. And if suppose you have a frame like this and one load is applied in this direction, okay, so beam mechanism can also occur in columns. Beam mechanism can also occur in columns. So if one plastic hinge form at this point, one plastic hinge at from this point, one plastic hinge at form at this support, then this is also a beam mechanism. So beam mechanism can form in both vertical and horizontal members. So beam mechanism can form in both horizontal and vertical member. Okay, and remember that this is the partial collapse, right? Next independent mechanism is sway mechanism. Sway mechanism. Okay, in sway mechanism, the frame, the collapse of the frame will look like this. Okay, so one plastic hinge will form at this point, one at this point, one at this point, one at this point. So this is our sway mechanism. Okay, so this is the sway mechanism. In this, you can say that the structure is sway. There is a sway to the left. Okay, sway to the left, right? So this is a complete collapse of the structure. Complete collapse. Okay. So now you can see that this is a sway mechanism. Okay. So we need to identify, if you have this structure, this is symmetrical structure. Okay. And if you are applying the vertical load exactly at this point W, which is equidistant from which is also symmetrical about this axis, then this frame is not sway frame. This is a non-sway frame. So in this, no sway mechanism will be there. No sway mechanism will be there. Okay. So this is basically the sway mechanism. Next mechanism is basically the combined mechanism. Okay. And in all the mechanism, we are considering the axial rigidity of members. Okay, axial rigidity of the members we are considering. Remember that thing, because members we are considering actually rigid. Okay. Next mechanism comes is combined mechanism. Okay, so next mechanism is combined mechanism, right? And this is very, very important thing to understand this combined mechanism. So in combined mechanism, basically what we are doing is that we will be combining our sway mechanism and beam mechanism. Okay. So in combined mechanism, if let us suppose this is our simple frame structure, and if we want to show that what will be the combined mechanism look like. So in combined mechanism, and this load W is applied, the vertical load W is here acting at the center, and W from this left side. Okay, so when this frame is under the combined mechanism, when there is combined mechanism in this frame, and we know that 4 plastic hinges are required basically for complete collapse. So when there is a combined mechanism, so this frame will deform like this. In this you can see that there is a sway mechanism, plus beam mechanism. Beam mechanism is this horizontal member, and as a whole this structure is swaying to the left. So this is basically the combination of the combined mechanism and the beam mechanism and the sway mechanism. One plastic hinge will form at this point, one plastic hinge will form at this point, one plastic hinge at this point, one plastic hinge at this point, right? So this is A, this is C, this is D, and this is E, right? Now you can see that the plastic hinge is not forming at this B point, at B we are having cancellation of hinge. Plastic hinge is not forming on this point. Why? Okay. Now this is the most important thing in this problem, in the combined mechanism. Why plastic hinge is not forming on this B point? Okay. So why plastic hinge not forming on this B, right? B point, this B joint. Okay. What happens is that net bending moment at B will be less. Out of these 5 points where the plastic hinge can form, net bending moment at B will be very less. Okay. This we will be seeing now. Now let us suppose we are having this frame, this symmetrical frame. Okay. And you are applying a load W at this point. See it very carefully. This is a very, very important concept. Okay. So when this frame will bend, a deflection diagram okay, a deflection diagram will look like this. Okay, a deflection diagram will look like this, right? When this frame is vertical loading, when the vertical load is applied at the center, this frame, this is the bending moment diagram. This is the deflection diagram. And in the deflection diagram, you can see that this portion will be in tension, right? This portion will be in compression. Similarly, at this point, this portion will be in tension, this will be in compression. Here also, this will be in tension, this will be in compression, this will be tension, this will be compression. Right? Okay. And if you draw the bending moment diagram of this for this condition, it will look like this. the bending moment diagram will look like this. Okay. So now this is the thing, right? Now you can see that now if you apply the horizontal load to this case, horizontal load. Okay, first we are applying just what you can say that we are using the principle of superposition over here. First we applied this load W, then we are applying this load W in horizontal direction. We'll be seeing what will be the deflection diagram for this case, right? So in this case, the deflection diagram will look like this. Okay. Now by seeing the deflection diagram, you can see that at this point, there is compression, and there is at this point there is tension. Okay. Above this line, above this line, there will be compression, and below this there will be tension. Okay. So this is the case. If this frame is deflected, it will look like this. Okay. Here there will be what you can say that there is compression, tension. Okay. So after some time, this is point of contraflexion. Okay. So basically after this point there will be compression outside. Okay. Here tension is inside, right? So now you can see that if you compare these two things at this, just compare. This is, let us suppose, B dash, and this is B. Just compare B and B dash. Let us suppose this is B dash and this is B. Okay. Here you can see that this phase is in compression, this is in tension. Here this opposite is happening. This is in tension, this is in compression. So moment are basically, the net moment is basically reduced. So net moment is reduced. Here you can see that this portion is in tension, this is in compression. Similarly, this is in tension, this is in compression, this is in tension, this is in compression. So these two will add. These two will add. So net moment at this point will be more as compared to this point. Right? So by seeing this thing, by looking at this deflection diagram, we can say that the net bending moment at this B point will be less. Okay. And also it depends upon the magnitude of these two loads basically. Okay. So if this load, suppose W is very high, very high. If let us suppose if this is W1, this is W2. If this W2 is load is very high, so then there will be only plastic hinge will form. Then there will be only one beam mechanism will be there. Okay. So that is a different case. But here we can say that the net bending moment is coming less at this B point. Okay. Now here also you can say that here this is compression, here this is tension. Why the plastic hinge is forming at this point? Why? Because due to this load, the bending moment due to this loading system, the bending moment will be very less at this support. Okay, very less at this support. But when you are applying a W load at this point, the bending moment at this support will be very large. Okay, so this net will be more as compared to this. Okay, so moment, if you combine this moment at A, so this will be more than B. Okay, so this is why the plastic hinge is not forming at this B point, right? So this is a very important concept. You need to realize this thing very carefully. You need to understand this thing very, very carefully. Okay, why plastic hinge is not forming at B. Okay, so this is basically our combined mechanism, right? So next is we are coming to this problem. And we will be solving this problem using kinematic method, because kinematic method is very easy method as compared to the static method. Right? Now, let us first talk about beam mechanism. Beam mechanism. Okay, so beam mechanism will take place in the member BCD. Will take place in the member BCD. Okay. So now, when the plastic collapse is taking place when there is a beam mechanism in this member BCD, so this member will deflect. There is a plastic hinge at this B, this C, and this D point. So it will deflect like this. Okay. And this is during this deflection is basically during collapse. Right? So if we enlarge this figure, this is one hinge at B, this is at D, and this is at center C. So it will deflect like this. This is during collapse. Okay. This deflection, let us suppose, is delta. This is theta. This load is acting at the center, so this will be also theta. Okay. This is alternate angle, this will be theta, this will be theta. So here the direction of rotation will be this, like this. Here the direction of rotation will be like this. Here the direction of rotation is like this. Here the direction of rotation will be like this. Okay. So direction of the moment will be opposite to this rotation. Here the direction of MP will look like this. Here MP will act in clockwise direction. Here MP will act in anti-clockwise, and here it will be acting in clockwise. So this is how you decide the direction of the plastic movement. Okay. Now you need to apply basically internal work done plus external work done equals to 0, and this is via principle of virtual work. Principle of virtual work. Okay. So internal moment we will take positive. This thing we have already discussed, right? So or you can write is that internal mod internal work, because internal work will be negative, mod is equals to external work. Okay, internal work is negative. I am saying on the basis of that MP is opposite to its rotation direction. Okay, generally in books they will write that the work absorbed is also positive. That is also, you can say that statement is also correct. That this you are applying this load, you are giving this displacement delta, and this delta displacement, the work done due to this delta is absorbed in this hinges. Okay, so that will be also a correct statement. That is also a correct statement. So you can write MP into theta here plus MP into theta here, right? I am taking mod sign, that's why I am not showing negative sign. Okay, plus MP into theta at this point, and again plus MP into theta equals to, what will be the actual virtual work? W into delta. W into delta. There is no work done due to this load, because there is not any sway. The deflection is in vertical direction, so this work this load cannot do any work. Okay, so this is the case. So delta you can replace with theta. So delta I can write delta over med 2 equals to 2 theta. Okay, and this delta is very small. I can write tan theta equals to theta. Okay, tan theta is approximately equals to theta. Okay, so 4 mp into theta equals to w into 2 theta. Theta will cancel out each other. 4 into mp. What is the value of mp? mp is 200. This is divided by 2. This is 2. So from here w is coming out to be 400 kilonewton. Okay. So what is meant by that is that to make the beam mechanism, for the beam mechanism, the W load should be 400 kilonewton. The W load should be 400 kilonewton, right? So when there is a beam mechanism, at in member BCD, so W load is 400 kilonewton. Okay, so this is the case when there is a beam mechanism in this horizontal member BCD. Now we will be considering the sway mechanism. Now we are considering the sway mechanism. Okay, so in sway mechanism, this, as you can see that this horizontal force is acting towards left, so this will also sway towards left, right? So when it is swaying towards left, when there is sway in left direction, so this will deflect like this. This frame will deflect like this. So one plastic hinge will form at A, one at B, one at C, one at D, and one at E. Okay, right? So now, and here this W load is acting. Here also this W load is acting, right? So when this member is swaying towards the left, right? So this deflection is remembered during collapse, right? This deflection is during collapse. Okay. So when this is swaying to the left, okay. Initially, let us suppose this is the position of the frame. Now it is sway to this direction by delta 1 amount and delta 2 amount by here. This dash is original position of member, original position of this frame. Okay. So this is the original position of the frame. Now it is deflecting towards delta 1 towards left, and here also it is deflecting delta 2 towards left. Okay. As we are considering the members are actually rigid, members are inextensible, or you can say that members are actually rigid. Members are actually rigid. So that means delta 1 should be equals to delta 2. Okay. If delta 1 is not equal to delta 2, then there will be some force in this direction, horizontal direction. Okay, so that's why we are considering this member as axially rigid. So that force we need not to consider that force. So this delta 1 should be equals to delta 2, because we are considering the members are axially rigid or members are inextensible term. This term we have studied in when we are discussing about the kinematic indeterminacy of the structures, right? So this delta 1 should be equal to this delta 2. Okay, this is 4 meter, this is 2 meter, right? So if I want to calculate the relation between this theta 1 and this theta 2, it will be 4 theta 1 will be is equals to 2 theta 2, because delta 1 is equals to delta 2, right? From here 2 theta 1 is equals to theta 2. So this is the relation between this theta 1 and theta 2, right? And let us calculate the direction of the moment, plastic moment. Okay, so here at this point the moment direction will opposite to the rotation, so this is MP. Here the rotation is in, what you can say that in clockwise direction, so moment will be in anti-clockwise. Here again the rotation is in clockwise, so moment will be in anti-clockwise, MP. Here also the rotation is in clockwise, so moment will be in anti-clockwise, MP. Here also the rotation is in clockwise, so moment will be in anti-clockwise. Okay, so direction of the plastic moment is decided, right? So the plastic moment is anti-clockwise at in this 4 location. Okay, now we need to apply what will be the principle of virtual work. Principle of virtual work. So if you apply the principle of virtual work, external work done will be equals to plus internal work done is equals to 0. So I can write external work done with mod of internal work done, right? So let us come to first calculate the internal work done. It will be MP into theta plus, here again MP into theta plus, here again also it will be MP into theta 2, plus at this point it will be MP into theta 2. Okay, and this what is the value of the external work done? It will be W into delta 1. No work is done by this W load. Okay, so I can write 2 MP theta plus 2 MP theta 2. So theta 2 is basically twice theta 1. So this is 4 MP theta, and this is W into delta 1. Delta 1 I can write, delta 1 is 4 into theta 1. So this equation will be W into 4 theta 1 plus 6 MP into theta. Theta 1 will cancel out each other, right? So W will be equals to 3 by 2 of MP. Okay, so MP is 200. So W will be 3 by 2 into 200. So this will be 300 kilonewton load. Okay, so you need to calculate the work done. Okay, work done, internal work done will always be positive. Okay, so you just need to equate what is the external work done. External work done is basically W into this delta 1 in this direction. Okay, W into this delta 1, right? So W load is coming out to be 300 kilonewton when there is sway mechanism. Okay, now let us calculate when there is a combined mechanism, what will be the value of W. Okay, now consider combined mechanism. Okay, so we have already discussed how this frame will deflect in combined mechanism. Okay, so let us suppose if this is our frame, right? So in combined mechanism, we already discussed no hinge will be there, no hinge formation, no hinge. Okay, so hinge will be forming at this point, under this point load, at this joint and this support. Okay, so the deflection diagram during collapse will look like this. Okay, will look like this. This is hinge, right? When there is no plastic hinge between no plastic hinge formation at this B point, then this joint is a rigid joint, so this angle will remain 90 degree. Okay, and again this delta 2 will be equals to this delta 1. Okay, because we are considering the combined mechanism. In combined mechanism, sway is there, beam mechanism is there, so this delta 1 should be equals to this delta 2, because we are considering member are actually rigid. So this delta 1 should be equals to delta 2. Members are actually rigid or inextensible, right? If this is the case, let us suppose this angle is theta. So let us enlarge this diagram. This is, let us suppose, initial. Okay, so when this will sway, when there is a combined mechanism, it will look like this. So this delta 1 will be equals to this delta 2. Okay, this angle is 90 degree, this angle is 90 degree, right? So let us suppose this angle is theta, this is 4, this is 2, and this is theta 2. So what will be the relation? This delta 1 is equals to delta 2, so I can write 4 theta 1 is equals to 2 theta 2, okay, through Pythagoras theorem. If you apply the tan law over here, I can write 4 theta 1 is equals to 2 theta 1. Okay, because this delta 1 is equals to delta 2. Okay, so from here 2 theta 1 is equals to theta 2. This relationship we got through this condition when delta 1 is equals to delta 2. Okay, now if you draw one perpendicular over here, this angle is also theta, right? Alternate angles. This is 90 minus theta, so this will be theta. Okay, and let us suppose this deflection is delta 3. This deflection is delta 3. So I can write this distance is basically this is 2, okay, because we are considering members are actually rigid, so this is also equals to 2. So I can write this delta 3 is equals to 2 theta. Similarly, this delta 3 is equals to, let us suppose this is theta and this is theta dash, 2 theta dash. So delta 3 will be equals to delta, this is common to both these terms. So 2 theta is equals to 2 theta dash. So this 2 will cancel out. So this angle will be equals to this angle, right? And if you draw the perpendicular, so this will be theta 2. Okay. So here the direction of rotation is clockwise, so moment will be anti-clockwise, MP. Here the direction of rotation is anti-clockwise, so moment will be clockwise. Moment will be clockwise. Similarly, here the direction of rotation is clockwise, so moment will be anti-clockwise. Similarly, here the direction of rotation is clockwise, so moment will be anti-clockwise. Okay. So now just apply the first. You need to calculate internal work done, then external work done. Then you sum those things and equate it to 0. So for the principle of virtual work, through the principle of virtual work done, I can write principle of virtual work done. I can write internal work done plus external work done equals to 0. So external work done is equals to mod of internal work done. Internal virtual work done. Okay. So if you calculate the internal virtual work done, at this point it will be MP into theta. I am not considering negative sign because I have kept mod sign outside. Okay. Plus, if we come to at this point, here is also one plastic hinge is forming. So rotation is clockwise, moment will be anti-clockwise, MP. Here also this is anti-clockwise, so moment will be clockwise, MP. So this theta will be equals to this theta dash will be equals to this theta dash, and this theta is equals to theta dash. Okay, so MP into theta plus MP into theta plus MP into theta dash plus here again MP into theta dash, then again we come to this point plus MP into theta 2, okay, plus MP into theta 2 is equals to what is the extra? What will be the external virtual work done? External virtual work done will be this W into delta 1 plus W into delta 3, right? Okay, so this is theta, this is basically theta 1, this is also, this will be theta 1, so theta 1, okay, this is MP theta dash, MP theta dash, MP theta 2, MP theta 2, okay. So what is the relation between theta 1 and theta 2 is twice theta 1, and between, this is theta 1 dash is equals to theta 1, okay. So I can write MP into theta 1 plus MP into theta 1 plus MP into theta, because theta 1 dash is equals to theta 1, sorry, theta 1 dash is equals to this theta 1 plus MP into theta 1 dash, theta 1, what is the relation between theta 2 and theta 1? It will be MP into twice theta 1 plus MP into twice theta 1, and this will be equal to W into delta 1 plus W into delta 3, right? So this is how you write the virtual work done equation. Okay, this is very, very important. Okay, we have already this thing in detail, right? So this will be equals to 1, 2, 3, 4, 6, 8. So this will be 8 MP into theta 1 will be equals to W into delta 1. Delta 1 is what? Delta 1 is 4 into theta 1 plus, what is the value of delta 3? Delta 3 will be 2 into theta 1. So W into 2 into theta 1. So this will be 8 MP into theta 1. So this is 4W theta 1 plus 2W theta 1, right? So this is 8 MP into theta 1 equals to 6W theta 1. Theta 1 will cancel out each other. 8 into 200 divided by 6 is equals to W. So if you calculate this value comes out to be 200 divided by 3 into 4. So this value W comes out to be 266.667 kilonewton. Okay. So now if you compare, now you have result from all three mechanisms. Okay, we have calculated W value through all three mechanisms. One is W 400 kilonewton when there is V mechanism, 300 kilonewton when there is sway mechanism, and 266.6 kilonewton when there is combined mechanism. Okay, so which mechanism is critical one? Critical one will be that mechanism in which W will be less. Okay, so W will be less for this mechanism, right? For this combined mechanism. So combined mechanism is critical over here. Okay, so total collapse, so the collapse load will be 266.67. So this loading system will result in combined mechanism. Okay, and this is the critical part. Okay, so guys, I have discussed this problem in detail. So if you have any doubt in this lecture, you can write in the comment section. And the most important part in this lecture, why the plastic hinge is not forming on this B point. Okay, and what is the role of the combined mechanism over here, and how to write this virtual work done equations. That is very important part. Okay, so in the next lecture we'll continue this problem and we'll be seeing how to draw the bending moment diagram, how to draw the bending moment diagram during the collapse. Okay, and how to check the yield conditions, and how to check the yield condition and to get a true collapse load, whether this 267.6 is true collapse load or not. That we have to check, and that thing we will be doing in the next lecture when we will be drawing the bending moment diagram. We will be calculating all the reaction forces and we will be drawing the bending moment diagram, and through that we will be check whether this is a true collapse load or not. Okay, till then you can look into this problem. Okay, so guys, thank you very much. We'll meet in the next lecture.